Okay, let's see. Roger is telling me we can get started. So I'm going to turn on my camera. Okay. Hi. Yeah, feel free to turn on your cameras as well. So I'm Katharina. I'm an assistant professor in the computer science department, a little bit obviously. And yeah, I'm working mostly on natural language processing and machine learning. And as far as I understand, we have a group here of current or prospective master students. So usually what I say, and what you've maybe seen if you've looked at the website of my group, is that master students work with one of my PhD students on a project that either they or the PhD student or both together define. So basically, this means that if you're interested in the work done in my group, you should think about who of my PhD students you would like to work with and send them an email with me in CC and basically talk to them about their project, about your ideas, their ideas, etc. And because this is how it typically works, I've asked 4 of my PhD students to please present their current and past work to you. So this is what we're going to do today. So we have here, I think, Abtin, Stefan, Ananya, and Adam. And respectively, they're going to talk about multilingual natural language processing, language grounding, who was next? So NLP for education and morphology, computational morphology. Yeah, so I think we're going to jump right in. If you have any questions during the presentations, you can ask them in the chat. If they're easy, I can answer them, or the PhD students can answer them when they're done with their presentation. In general, we're going to leave a lot of time for questions in the end, so we should have like 20 minutes for all collective questions. Just Abtin has to leave early, so Abtin is going to have questions directly after his presentation. Okay, any questions so far? Anything you need to know before hearing about projects? Okay, it seems good. Yeah, Abtin, do you want to get started?
Yeah, I'm going to turn off my video before I get started. But since I'm not going to have so much time for questions, if Katharina, do you want to keep an eye on the chat and interrupt me if something comes up?
Yeah, cool. I'm going to do that.
If everyone who's not me can mute themselves, please, that'd be great. Okay, can everyone see my screen, hopefully?
Yes.
Great, okay, so my name is Abtin. I'm a second-year PhD student working with Dr. Khan. For the past year, I've been focusing mainly on multilinguality and cross-lingual transfer with a specific focus on low-resource languages. And the main thing that I'll be covering is a paper that we got accepted to ACL 2021, which was looking at language adaptation in the case of multilingual models. So a tiny bit of background, jumping right into it. In recent years, pre-trained multilingual models have shown really strong zero-shot cross-lingual transfer performance. If you're familiar with models like BERT, which kind of follow this paradigm of pre-training and then fine-tuning, pre-trained multilingual models have a very natural kind of extension of that, where it's kind of just a multilingual version of it. So rather than starting with data from one language, we start with data from a bunch of different languages. This number can vary depending on the model, from like 15 to over 100. And just as in BERT, we'll pre-train using mass language modeling, or depending on the data, some other objectives as well. We'll pre-train the model on data from all of these languages at the same time. And then we can use this model to fine-tune it on data for a specific task. This example is natural language inference, and then we can evaluate it on different data. And so it's cross-lingual transfer because in this example, we're training here on English and evaluating on Spanish. And if the model sees no labeled target task data in Spanish at all during training, and the first time it sees examples to label is during evaluation, then it would be zero-shot transfer. So what are some benefits of these types of models? First of all, you can cover a ton of languages with just a single model. Previous methods for cross-single transfer depended on word embeddings, where you would have perhaps aligned monolingual embeddings for each language, and you might imagine that it gets to be kind of a hassle if you have different sets of embeddings for all the different languages. With this, it's just a single model. This is with the caveat that performance is not going to be the same across all the languages that the model is pre-trained on, and the performance is going to correlate typically with how well represented a language is in the pre-trained data. So if there is a larger percentage of the data allocated to a certain language, the performance is going to be pretty good. And if there's not much data in a language, then performance is going to be a little worse. And naturally, because it's a single model, zero-shot transfer is also quite simple. You train it once on a source language, and you can just evaluate it on the other languages that you're interested in. But of course, not everything is perfect. Some drawbacks of pre-trained multilingual models. First of all, if you have enough data in a language, a monolingual model will oftentimes work better. And intuitively, this makes sense because a monolingual model only has to really care about one language. It can afford to give more parameters and more kind of space and thought towards that language, whereas multilingual models have to kind of share the load across all the languages. Additionally, there's this thing called the curse of multilinguality, which says that as the number of languages increases, we hit a point, and after that point, performance on all of the languages will be limited. And for a model of feasible size, that point is, I think, around 100. And so there will always be some set of languages which are going to be unseen to the multilingual model. And these are languages which we don't have, which the model is not pre-trained on. And as I was talking about performance correlating with representation, the performance for these languages is typically kind of low. And the languages that are most likely to be unseen are going to be low resource languages because they're exactly the languages which don't have enough data available online to pre-train on. But they kind of fall into this weird area where they might not have enough data to train their own monolingual model, and multilingual models don't work super well on them. But if you do want to get, your best bet for getting good performance is to start with a multilingual model. And rather than thinking about adding these languages during the pre-training, we can take an existing multilingual model and adapt it. And this is a concept really similar to domain adaptation. And in our work, we looked at 3 commonly used methods. The most basic approach, which is treated normally as a baseline, is called continued pre-training, where you take the pre-trained model, pre-train it more on data that's only in the language that you're interested in, and then fine-tune it like usual. You can extend the vocabulary and add additional tokens from languages that maybe do not have a good representation in the model's tokenization. Or there is a framework called MADX, which makes use of adapters. And these methods have all previously been shown to improve performance on these unseen languages. Specifically, vocabulary extension and MADX kind of advertise themselves as being improvements over continued pre-training, which is treated as kind of the most basic and baseline approach. There is a limitation of these adaptation methods in that they've all been evaluated using resources which aren't actually available for the majority of the world's languages. An example is Wikipedia. It's only available for 320 languages, which is around less than 5% of the total languages, or Common Crawl, which is available for around 3%. And so this means that in practice, the languages which would benefit most from language adaptation are likely to be exactly the languages which don't have the necessary resources to implement these methods as described. So the languages which might need these methods the most, we actually don't know what performance is going to be like for them. And this was the motivation for our work, where we asked, how do these adaptation methods perform in an actually real-world scenario? And to simulate this, we were looking specifically at the performance if the only available text for a language was the Bible. The Bible is available for around 1,600 languages, but on the other hand, it's very limited in both the size and the domain. And our experimental setup covered 30 languages, and we considered 2 tasks in order to evaluate the different methods. The first task was part speech tagging, and all of the methods, all the adaptation methods improved performance. But we can see that the continued pre-training methods kind of consistently outperformed vocabulary extension and adapters. Part of speech tagging is kind of what I would consider personally the easier of the two tasks. The second task we considered was named entity recognition, where interestingly here, the vocabulary extension and adapters actually harmed performance, the baseline performance. And the only way we were able to improve performance was by doing the continued pre-training. And so we found that kind of in general, on average, when the available data for pre-training is limited, the best performing adaptation method is actually the simplest method, which was the continued pre-training. And as we were kind of doing this, we thought about how we can generalize this experiment. And one of the main limitations that kind of was imposed on us was the downstream tasks we use for evaluation. Part of speech tagging and named entity recognition are kind of lower level syntactic type tasks that depend on the structure mainly of a sentence. To get a more complete picture, it'd be best to kind of have a more semantic, higher level task available. But unfortunately, for the languages that we're kind of thinking about, these sort of data sets aren't available. And these tasks include stuff like question answering or natural language inference, which supposedly require some higher level semantic understanding of what's going on in a language. And this was kind of a motivation, and I'll keep it in the back of our minds. And I briefly want to talk before finishing about AmericasNLP, which was the first workshop on natural language processing for indigenous languages of the Americas. This was a workshop that Katharina co-organized, and I helped organize a shared task on machine translation that was held kind of within the workshop. And so, as I mentioned before, there are 7,000 languages spoken across the world. Looking at the distribution, we can see that there are a lot in South and Central and a little bit Northern America, a lot in Africa, and a lot, again, in Southeast Asia. For Africa, there is an NLP community called Masakane, which focuses on these languages. But for languages in the Americas, there isn't a kind of, or there wasn't a group of people that were dedicated to looking into it, which was another motivation for AmericasNLP. And the shared task within AmericasNLP was a task on open machine translation. Oh, sorry, there were 600 languages in South and Central America with over 20 million speakers. And we covered, I think in that shared task, we covered 10 languages, and these were kind of spoken throughout South America, Central America, and Mexico. And so the task was machine translation. We knew that there were no evaluation data sets for higher level tasks in these languages, in like low resource and unseen languages. So the way we set it up was we took sentences from the Spanish cross-lingual natural language inference data set and translated them into the target language. And doing this served kind of a dual purpose in that we could use the sentence pairs for machine translation, but if we kept the natural language inference labels, we could then use this new data set as a sort of natural language inference data set. And this allowed us to kind of experiment with a bunch of different baselines and basically start to extend the 1600 languages paper to more tasks and see how the results kind of hold for more difficult tasks. And this work is still ongoing, but yeah. And so that was all I wanted to cover today. If anyone has any questions, feel free to ask. I'm also, feel free to email me as well. I can put that in my email in the chat. So there's a question in the chat, why did adapters harm the named entity recognition? I don't want to give any concrete answers as to why. My personal belief is that when data is limited, introducing new kind of randomly initialized parameters might be harmful because we don't have enough data to train them, which is why adapters work well when you have enough data, because then you can train the randomly initialized parameters. That's maybe one reason why adapters didn't work well. Yeah, no problem.
Thanks, Aptine. Are there any other questions? If not, so Aptine is the person for anyone interested in creating data sets for low resource languages, potentially doing MT, so machine translation for indigenous languages from the Americas, in general, transfer learning, pre-training, etc. Aptine, anything else that, or anything else you would like to work on with a student?
Any type of adaptation would be interesting. I think we're moving into general adaptation research as well. So just domain adaptation.
So domain adaptation, for those who don't know, is basically if you have a general model that's trained on, let's say, Wikipedia, and you want to apply it to something very specific, like let's say you want to read medical records, right? To like automatically analyze problems a patient might have that maybe the doctor was overlooking. Or you want to, I don't know, process some sort of like, okay, we're looking into like education as well, right, with Ananya. So you want to process text that belongs to a specific subject, like maybe physics. In that case, you would want to take the general model and somehow make it work better on that thing with like domain adaptation. Okay, yeah, thanks, Aptine. Should we move on to, I think Stefan is next. Stefan, I think you're muted.
All right, let me restart there. Hi everyone, my name is Stefan, and today I'm going to be talking about my research direction, which is really how we can approach a human-like understanding of language in machines. And before I start, I will preface, there's a lot of really useful NLP models that can do really great things, even though they don't understand language as humans do. But I think that there is a strong motivation to eventually get there so that we can have a strong kind of human-machine collaboration. So starting back at the start of my research, or going back in time, how NLP was developed, a lot of labeled text was used. Supervised learning has a clear inputs outputs to train on, and so this is kind of a clear first step. And this is where you'll start seeing things like your old corpus training on the Brown corpus, and it was really just calculating statistical patterns between n-grams and labels. Shortly afterwards, they realized that there's an abundant amount of unlabeled text, which is way cheaper and still contains a lot of useful information about how language exists in the world, which kind of brings the development of things like word2vec or glove and fast text that build word embeddings from a bunch of unlabeled datas. And then you can use these embeddings in kind of like a bag of word or an LSTM approach for downstream labeled tasks. And if you guys don't know about these, they're kind of core classical NLP methods, but I won't spend too much time on them today. And then we realized that we can do even better than that. Instead of just looking at individual words, we can look at entire sentences. So words like I'm the shore of a bank by a river and I'm withdrawing money from my bank account. The word bank would have the same embedding in word2vec, but obviously though they have drastically different meanings in those two sentences. And BERT was kind of the first model, not quite the first model, but the first like very popular model that took this into account and enabled embeddings for full sequences of text. And I'll spend a bit of time on BERT here because I think it's a very important part of NLP, the field of NLP currently, as well as kind of my initial work. So BERT is a very large pre-trained transformer trained on two tasks: mass language modeling, which essentially means you mask out a word in your sentence and then you ask the model to predict it. So for example, my mask is cute and the model has to predict dog. And then the second one was next sentence prediction. And next sentence prediction is kind of what it sounds like. If you have my dog is cute and the next sentence is he likes playing, we as a human think that those are reasonable next sentences. However, if the second one was like, he ate with a knife and fork at a dinner table, you'd be like, okay, that's probably a completely separate sentence. I'm going to skip this for now. So when BERT came out, it got state of the art on 11 different NLP tasks at the times and kind of created a subfield in NLP called BERTology. And in the original results, next sentence prediction was shown to improve results. But a few papers came out and started contesting this. And this is kind of where my first research project came out, because I was looking at NSP and it made sense to me, but people were contesting it. And then I thought, well, can we create better tasks, essentially? And so this led me to my first project, which was this paper on losses for modern language models, which I set out to answer 3 questions. Is NSP, next sentence prediction, beneficial or detrimental to BERT pre-training? Are there better self-supervised tasks? And is there a best way to combine multiple tasks into BERT pre-training? So my baseline was kind of a BERT trained only on mass language modeling. And I trained on the same data as BERT, although with substantially less amount of data. So the same amount of, the same source of data, just less. And the first thing I compared was just a BERT trained on mass language modeling, a transformer trained on mass language modeling and next sentence prediction, and then one that had the split context of next sentence prediction, because obviously if half the time your next sentence comes from a different document, you're splitting the context, but without the actual loss of predicting whether it is from a different sentence. And then I tested 14 different self-supervised tasks. And I'm going to go quickly through here because this is a bit more of my past work. But essentially I found that next sentence prediction was too easy to solve, right? So instead of actually looking at the flow of text, you can just look, okay, the first sentence contains dog, the second sentence contains dog, and so we can solve it that way. And the cost of having to split the context half the time was more detrimental than the benefit of next sentence prediction. However, there are some ways to get around that, and there are some other tasks that follow the same logic that do substantially better. And then I tested 14 tasks, and I'm going to go through these. I'm just going to scroll through these because it takes some time. But at the end of the day, there was kind of 3 sets of tasks that I found really benefited BERT pre-training. The first one are word importance signals, so things like your TF-IDF, so term frequency, inverse document frequency, which is kind of a signal of how important words are. The second one were inference signals, so these were tasks that resembled what next sentence prediction was trying to do, but without the costs. And the last one were tasks that directly tried to cluster similar word embeddings or similar sentence embeddings. I then looked into combining tasks, and I found that as long as you include mass language modeling, it is beneficial to combine multiple tasks, and it's almost always better than using any single task. And at the end of the day, I was able to outperform BERT base using less than a quarter amount of the training data on the GLUE benchmark, which I was pretty happy about. But coming out of this project, I was starting to question if these models really understood language, because we're just training them entirely on text. It's like trying to learn language by just reading books and hearing the radio, but never actually going out into the world or interacting with anyone. Which led me to do some research of my own, and I found a few very interesting papers that I think helped me refine my ideas. So this first paper provides a working definition of understanding as the ability to recover the communicative intent from an utterance, which just means, so essentially if I say, I dropped my glass, you guys are all able to map that to a time where either you've seen a glass drop or you've dropped a glass yourself, and you can create a mental scene and generate about possible outcomes just from that utterance. But language models don't have this experience in the real world, so they can't actually leverage any previous experience for their understanding. Which kind of led me to my next project of, okay, if they don't have these experiences in the real world, are they able to understand and reason about real, text that describes real world events? Which led to my paper, Physical Reasoning of Objects Through Space and Time, which was accepted to ACL findings this past year. And the main motivation was to design a set of questions that will probe whether a model is able to understand and reason about the physical world. So one of the issues that more and more people are seeing is that these really big language models succeed at tasks, but often they succeed in unintended ways. So they find data correlations that are not at all how us as humans would solve the task. And to avoid this, we actually decided to handwrite all the templates to make sure that none of the models would have seen this exact these sentences before, and we probed all the models in a zero-shot way, which is definitely more challenging. But humans are probed in a zero-shot way all the time, and we do very, very well at it. So, you know, to give you a general idea of what these questions look like, it'd be things like a person throws a ball straight into the air. Immediately after reaching the highest point in its trajectory, the ball is moving towards the blank, the ground, the sky, the left or the right. And a human would likely be, okay, after the highest point, you're starting to move towards the ground. Or you have a book and a coin are placed on either sides of a perfectly balanced seesaw. The side of the seesaw with the blank moves down, right? It'll always be the one with the heavier one. So the side with the book is going to move down. However, what we realized after probing a wide range of modern language models at varying sizes is that most current language models are terrible at this. The highest score for a general model, so that's not like specifically trained for multiple choice question answering, was 31.8, which a random score is 25%. And actually on a few of the topics, it does worse than random. Beyond that, we also tested Unified QA, which is a model that's specifically trained on a lot of, you know, science-related text, and is trained for multiple choice question answering. And even there, and actually this is an old table, but the highest score it achieved, even for its 3 billion size, was 46.7%, which is still very, very mediocre for a model of that size trained for this reason. Now, beyond just like the overall results, we actually analyzed a few other things. So the first thing we analyzed was if we inverted the sentence, inverted the superlatives in the sentence. So here, for example, a person is trying to stack eggs, books, balls, and flowers. The blank are the easiest to stack. We can ask the inverse of this by saying the blank are the hardest to stack. And if we do this, we found that models have a very strong preference for one side versus the other side, which is unlike humans. Humans generally, if you can identify the biggest object, you can identify the smallest object relatively easily. The other thing we realized, so we have these context questions where we provide 4 objects and then we ask something about the scenario. We tried just changing the order of the objects presented, and that had a very big difference on the impact, where if it's in the first or last position, they would have 35–40% accuracy, but in the third position, they drop down to a 10% accuracy. And humans definitely have biases when they read things, but it's clearly not this strong. And we're almost always able to reason past our biases. And the last thing we looked at was scaling, right? There's this huge thing. You look at GPT-2, did very well, and they just, you know, increased it 100-fold for GPT-3. And we're like, okay, well, could you just solve this if you just made things bigger and bigger and bigger? And generally there was a slight trend upwards, but there's a lot of times where smaller models did better than bigger models. And even big models, you know, you'd have a 10x increase in parameters for a 3 or 4% increase on it. So to actually succeed on this data set would either require a model that is beyond our current comprehension, or my current hypothesis is this just won't be solvable through scaling models alone. So this kind of brings me back to like, okay, how do we teach models to understand language like we do? And I think the core of that for me is we actually have to provide language models with the experiences that we have so that they can develop the concepts that we have, so that when we speak utterances, they can retrieve those concepts and actually understand what we're saying. And to me, the best way to do this is through robots and embodied agents that interact with the world. So embodied agents may a bit of a broader term and can help with these easier scenarios, right? You can maybe teach some concepts in a grid world of like turning left or right or going to colors and shapes. But I think my end goal is to go to robots. Robots have a huge array of sensors and can gather data like we do and can interact in the actual world that we interact with. And so the robots are going to be the ones that can develop concepts the most similar to us and give the richest understanding of language. Yeah, so my past work has been understanding why we can't understand, why current models lack a human-like understanding of language, and my future research is how we can actually accomplish that. So if you guys are interested in that, let me know. Reach out to me. I will drop my email in the chat. And I think that for the sake of time, just maybe better to email me questions because I think we're running a bit behind.
Thanks, Stefan. But I think we're okay. Also, Adam said he had an emergency, had to leave, so we're going to have one presentation less. And there's one question in the chat now, so if you want to answer it, go ahead.
Yeah, of course. How would you contrast? I think there's a first question, was it compared against the human performance for the same? So I think we did do a, I don't think we, I mean, there's because of the permutations that were questioned, there's something like 18,000 permutations of the questions. However, we did do a human performance of like ranking the objects under certain constraints. And I think we had a 95% plus agreement on it. So humans were able to actually accomplish these tasks relatively simply. Next one, how would you contrast experience and knowledge in context of the same? I mean, to me, knowledge is a lot more abstract. I think that there is a huge amount of knowledge, and I think that knowledge is perhaps, to me, I think you require concepts to then build knowledge. So for example, like knowledge, you could say, and this comes from a paper, but Dante was born in 1865. But if you don't have a concept of, a birth date, or you don't have a concept of time, you're never going to understand that knowledge in the first place. So I think that, yeah, there is a huge amount of knowledge, and I think there's a lot of work in terms of like how we can, use knowledge bases to enhance language models. I haven't looked, I've read some papers there, but I haven't looked that much into it itself. I think that there is a relation between concepts and knowledge, but I think to me, concepts are kind of like the underpinning of all knowledge and understanding. Did results model of PROS also helped improving BERT in learning the embeddings of the sentence creations? So PROS was just a probing data set, so we didn't actually train anything on PROST. In fact, the goal with PROST is I want to train something that's simulated in the real world with language, where you have this multimodal experience, and then you can bring the language component back, and it should be able to solve PROST in a zero-shot manner, similar to the way that the humans do. I think that my biggest thing with training just on text is that I'm scared it'll just pick up on correlations in the data. So I'm sure you could have a model 16 on PROST if you trained it on similar enough text. But that's not my intention here. My intention here is to build transferable concepts that are understood through language. And I think that's all the questions. If anyone would like me to, clear things up on that, I'm happy to. If you want a further discussion on that, send me an email. I'm happy to discuss my work anytime.
Thank you. Okay, Ananya, are you ready?
I think so. Okay, can everyone see my screen?
Yes, we can see it.
Okay, so hi everyone. My name is Ananya. I'm a second-year PhD student working with Professor Khan on natural language processing. My research interests are in building computational models to understand and generate content specifically as applied to educational applications, such as classroom settings. So I work closely with the NSF AI Institute on student AI teaming, which is led by several faculty here at CU. So today I'm going to give a brief overview of what we do, as well as a case study of a specific project that I recently worked on. Sorry, I'm just having a couple of issues with slides moving between my monitor and my camera. Just a second.
Maybe I'm trying to find it, but my computer also has some issues. Rodri, you by any chance have the link to the AI Institute website, and could you post it in the chat?
Sure.
Thank you.
Okay, so no one can see my slides now, right?
No, you can't see them.
Okay, so you can see it now. I think, so I'm forced to use the Keynote view in like both screens. Okay, cool. Okay, so does this work?
So now we see your notes quite like big and your slides are very small.
That's the presenter view. Okay, so ideally I'd have it reversed with the big slides on my actual computer. I'm just gonna unplug my monitor if this doesn't work. Okay, and speak without notes, I guess, which is fine. Okay, so so the NSF Institute for Student AI Teaming, our goals are to develop a system that can serve as a partner to students in a classroom in their learning process. So what we want from this is, okay, sorry, again.
That's good.
Yeah, okay. So what we want from such a system is to engage students to speak more in a classroom, especially in the process of collaborative learning. And we also want the system to be able to ask and answer questions related to the content. So asking questions in order to provoke a student to think deeper about concepts that are being taught and answer questions that a student might ask to the system. So yeah, so ultimately one of our main goals is to get the student to speak more in a classroom. Why do we want this? Theoretically, our motivation is based on studies in like learning theory, educational research that shows that active participation in a classroom and not just passively listening is essential for deep conceptual learning. So active participation refers to actions such as asking questions, relating to ideas or questions posed by other students, reflecting on past content and like making connections, as well as providing evidence for answers that they give. So by deep conceptual learning, we mean the knowledge and the understanding of content that's required to solve problems or like construct complex arguments, and in the best case, teach a concept that they've learned to other students. So yeah, so why is this a challenging problem to generate utterances that can accomplish this? So as we all know, like dialogue systems in NLP have been like an active area of research, and they broadly work for like task-oriented dialogue systems that you might interact with on your phone, or open domain dialogue systems such as chatbots that you can talk to, such as you would talk to a human. So why can't we use something like that to generate utterances in our classrooms? So one of the issues with like open domain dialogue systems is that their goal is to have an engaging conversation with the user. And so the utterances that they make tend to be extremely broad and open-ended. On the other hand, they might produce like completely irrelevant utterances, such as, I couldn't hear you. And in the worst case, they could generate utterances that are unsafe in a classroom environment because of patterns that they've learned from the training data. This could be, either like biased content or it could, I mean, these are students, so they might like provoke the system to like generate profanity and stuff, which is something we do not want in a classroom. The third point is that with such a system that's taken off the shelf, we have no control over the kinds of interventions it might make. So we have some specific points where teachers typically intervene. So in a group discussion, a teacher might ask a student how they arrived at an answer, or they might ask another student what they think about like another student's ideas. And we want that level of control over what the model is going to do. So to get there, we propose a framework for generating utterances that involves first identifying the kind of intervention or like talk move that is to be made, and then generating utterances that adhere to that talk move. So let's look at a small example. So this is a group discussion where these students are trying to solve a problem where, one student is saying 2 slices of toast are done in 2 minutes. We need to find out how long 5 slices might take. And another student says, I think the answer is 6. So this is an opportunity to intervene and get everyone to think about the steps that get you to such an answer. So we might want the system to say at this point, that's right, how did you arrive at that? So yeah, in order to like make interventions like this, we turn to a framework in education research called academically productive talk. So this was not proposed. Okay, so this was proposed by like Michaels and O'Connor in the citation below. It's been actively used by teachers in actual classrooms for more than 20 years in order to get students and teachers to have respectful and productive discussions. So they do this using tools called talk moves, which are basically utterance strategies. Given some sort of like conversational context, there are certain talk moves that you can make in order to have a productive discussion. So here are some examples of talk moves. So keeping everyone together and getting students to relate would typically be made by a teacher to bring like the discussion like on track or together. Restating and revoicing, they repeat something that a student has said for greater emphasis. Pressing for accuracy and pressing for reasoning is done when the teacher wants to make the student like come up with some answers or think deeper about something. And none and wait are like introduced by us for utterances that don't fall into any of the above categories. So in our recent like ACL findings paper, we proposed the task of future talk move prediction for such a conversational system, where the task is to predict the next talk move that should be made given a conversation history of what's happened in a classroom. Out of these 8 possible talk moves. Now, the gold standard for what the correct talk move is taken from transcripts of classroom discourse that are annotated for what talk moves the teacher actually used. So we propose a model for this task that we call 3E. Crucially, we encode 3 key pieces of information. First, we encode like individual utterances that occur in the conversation history. And then we encode the entire conversation history, like the representations that come from this GRU. And then we also find that encoding the history of talk moves in the conversation is really important for this model to perform well. So yeah, so this is our model for future talk move prediction. How does it perform? We run a small diagnostic survey with 2 human annotators. So in the confusion matrix here, the chart on the left, the leftmost is our model's performance, and the middle and the right are the 2 human annotators. So just like a broad overview sort of tells you that the model identifies similar patterns to what the human annotators do, especially the first and second. The kinds of talk moves that it finds difficult, such as, okay, so the numbers here, this is clearer in the paper, but so 7 and 8 stand for press for reasoning and getting students to relate, respectively, if I remember correctly. So there are some specific talk moves that the human annotator struggle with that the model also struggles with. And similarly, there are some talk moves that human annotators are also able to perform well, and the model roughly does reasonably well at those talk moves. But clearly, there's still a long way to go to attain like human level performance at this task. So what are some other problems that we're working on as part of like the NLP aspect of the NSF AI Institute? So I am part of a strand that pertains to like dialogue understanding and generation, as well as content analysis. So one of the main problems we have is we need to be able to detect who's speaking, know something about like the attributes of the student. Is this somebody who tends to speak a lot, or is this someone we need to encourage to speak more? There's like semantics and pragmatics. Semantics would be just sentence level meaning understanding that goes beyond just knowing what a word means. Pragmatics would be understanding implications behind something a student says, like are they being sarcastic, etc. So other problems that we're interested in is tracking if a discussion is going off topic and then generating utterances that bring it back on track. And yeah, the main strand is what I presented here, which is generating utterances that encourage discussion. So from the content understanding side, we're interested in ways to properly represent like an entire lesson or curriculum that would just be like a running text with a lot of figures. We need some meaningful way to represent it that can be understood by a computer. And as students speak, we also want to map a representation of their utterances with what we know about the lesson or curriculum. So are they truly understanding? Are they making mistakes? Ultimately, we also want the system to be able to answer questions that a student asks in class. Yeah, in relation to this work, there's actually another master's student who's working on question reformulation. So that's something if you're interested in similar problems. And broadly, following up to what Apteen and Katrina were saying, we're also interested in domain adaptation because pre-trained models typically are trained on domains like Wikipedia, which is different from the kinds of content we'd see here. So that's an important problem as well. All right, I think that's it.
Thank you so much. There were a couple of questions in the chat.
The gated recurrent units used were bidirectional. No, I don't think they were bidirectional. The problem is very open-ended. Different subjects will be trained the model differently. Yeah, that's actually a very good question. And that's a challenge that we are facing as well. Like, okay, sorry, just a second. So the question here is, there is sometimes no correct answer. That's absolutely true. Like teachers in different or in the same situation might make a different talk move depending on like other contextual changes. So yeah, I think one way to, I think that's, okay, so in like dialogue related tasks, that is always going to be a challenge because there's always different branches of like actions and events that you can have depending on like how your state changes. And it's not practically possible to collect data that sort of satisfies every like branch that you're going to see. So what we're trying to do is use the actions made by the teacher as one source of information for what you do in a particular, like given a particular conversation history. And it is true that, the model might make moves that are somewhat appropriate, but out of those appropriate actions, what the teacher makes is also one. And we're trying to see if it can learn at least one suitable like sequence of actions. So that's our focus while modeling and evaluating this. So
yeah, hi Ananya. No question. Just how do you see multilinguality playing a role here? Because the students may have different backgrounds, second language learners, and so on and so forth.
So I think that's definitely something we need to be aware of before the system probably, I don't know, gets deployed. But I also think that that's like a whole separate and extensive challenge that maybe needs many more years of work. And right now, the formulation of the system is to go into like Denver, like Colorado classrooms as, in a span of like 5 years. That's the duration of the AI Institute. So, that's not something that we're directly working on. So one other project that's like tangentially related, because you mentioned like second language learners of English, is we're working with researchers in the Institute of Cognitive Science on studying if language models that are trained on multiple languages exhibit similar patterns to like bilingual speakers. So investigating this could provide some useful directions for like generating educational material for bilingual speakers, which is something that could be useful to us.
Yeah, it's a very good question, right? Like, how do we make sure that the system, if it works at all, ideally works for everyone and not just for a selected subset of students? Yeah, it's highly relevant. It's just like, I mean, of course, that's like kind of a bad excuse, but it's just so hard to make it work at all that we're like a little bit postponing the even more difficult cases. Yeah, does anybody have any more questions? Now, also, like if you have any questions to Stefan, I think he's still here. I'm not sure. Yeah, he's here, so that would also be possible. Okay, alternatively, I also wanted to mention that I know that at least one or two of the people here have emailed us previously, but so there are some issues. So for example, like the one thing is on the website it's describing if you email us, you should include certain keywords in the subject. And basically the reason is just that we want to make sure that you at least got a little bit informed before you emailed us, because there are like so many people interested in like working with our group, and right here there are like 50 people here, right, that we can't just answer to like every email if the people don't put in at least a little bit of work first. So for all of you, if you're interested, check out the website, figure out what the keywords are that you should use, and then insert them into the subject line. Also, please, if you've already sent an email, just to be fair to everyone, right? We cannot just like make exceptions for some people, not for others. Yeah, that's a very bad note on which to end, actually. So what else can we say? I can talk a little bit about morphology if nobody has any questions.
I have a quick logistical question, if that's all right.
Yeah, sure.
So I'm mainly interested in doing ideally a PhD program versus the master's.
Mm-hmm.
Do we still reach out to people we're interested in the same way?
I see. So no, for PhD, it's different. So in that case, you still need a keyword in your subject line, but you can just send me an email and I can get back to you and we can discuss more. So there you don't need to include any other students, because if you start as a PhD student, you would get your own topic, right? So you don't need like a collaborator. Someone's asking, would it be possible to apply to both the PhD and the master's program? I believe in that case, but Rajri should maybe correct me. Yeah. You apply for the PhD, and if you're not selected, you could be offered a position in a place in the master's program.
Yes, so there's a question during application process where we say, do you want to be considered for master's if you're not accepted for PhD? And you would say yes, and the committee will review your application for master's. And if you get admitted to PhD, you can always pick up a master's on your way to PhD. So you don't have to submit 2 different applications for that.
Okay, we have one question for Stefan. Aren't there existing resources that define relationships between objects? And what do you expect their roles maybe to be in reasoning?
One second, I'm just reading the question over. Existing resources that define relationships between objects. Yeah, I mean, there's a bunch of knowledge bases and a bunch that define a lot of relationships. I think there's things beyond knowledge bases as well. To me, I'm not even at a point of defining relationship between objects. I don't think language models understand, the basic objects. So, it's great to know that an apple is edible. But if you've never actually interacted with an apple before, you might not really know what that means. In a similar way, like, can someone really understand color if they've never seen color before? Some birds can see ultraviolet. I would argue that I don't really understand what an ultraviolet color looks like, other than approximating it to my best interest. So yes, there are things that define relationships, but I don't think that helps you actually learn a concept. I think that's that once you have a concept, it helps you expand your knowledge. Hopefully that's satisfactory. I know that it's not a perfect answer. I think simulation is necessary. That's my intent, is to heavily rely on simulation. I think ideally you interact with the real world, but I think that's kind of a step after simulation. So I'm definitely planning on using simulations. I think the rest of the questions are not for me.
Yeah, I think there's one that's more general. I'm interested in getting a PhD and studying NLP. Which department would you recommend applying to? Linguistics, computer science, or other? I would recommend obviously the computer science department, because that's where I am and I want all the great students to come to my group. In general, it might depend maybe a bit more on, in terms of the work, it might depend maybe more on the area of the professor you're applying to. So maybe which department is a better fit is more like, in which department is the professor who you think is the best fit. But then there's some practical things. Maybe I actually don't know so well, but I would say computer science could give you maybe some benefits later on trying to find a job if you're not staying in academia. But I'm not 100%. I don't want to say anything wrong here. So I would say, like, content-wise, the best thing is to look at the professor's work. If we apply for the PhD program, is it possible to change our concentration from what we select our application later, or are we committed to that specific concentration? So I guess like a focus. No, in fact, I would say that probably many of the students that are currently working with me don't actually work on what they originally wanted to work on. So of course, it's nice to have an initial idea of what someone's interested in, but then typically during the application process, we discuss, and then we think about possible topics, including the ones that were on the application, but not limited to those, right? And then before starting, we kind of agree on a topic that might be any type of topic. And then even later, potentially you have a chance to change. So I think that hasn't happened so far, but theoretically you could. So it's very, very flexible, at least in my group. It's a little bit different if you're hired for a specific grant, but I'm not exclusively doing that, and I haven't so far.
And to add to that, Katerina, if I may, when you submit your PhD applications, you do get to pick 3 different advisors in your application. We say your first choice, your second choice, and your third choice. And during application review process, all 3 of them will review. If they see a better match with another faculty, they actually forward your application to another faculty as well. So there's a very intensive review that goes on. And once you're here also, you can always switch if the research match isn't there.
Yeah, so pretty flexible, basically. Any further questions? Okay, thanks for putting your emails. So that's great. Can master students get research funding? Rajri, so I know that master students can get TA positions that cover their tuition and give them some salary. They can get RA positions, but I don't typically give those. Right. So I only do this if I've worked with like a master student for an extended period of time. Other professors might handle that differently.
Yeah, so every lab is different, and so there are a few positions in the systems lab. I think the Aspire Center has some, so it depends on the faculty that you're interested in and the funding they have. And so if they have extra funding or they are looking for more research students, then at least maybe about 10 or 12 master students have been able to get RA funding, but it's not as typical.
Mm-hmm. Okay, should we wrap up?
Mm-hmm. We're over by 4 minutes, so maybe we should. Thank you so much, Katrina, for doing this. It helps a lot. You've seen the participation is so high in your presentation as always, and I'm sure students are very enthusiastic to learn more about your work. So thanks a lot, and thanks to all your PhD students as well.
Yeah, thanks so much to, I think, Ananya, who's still here, or anyone who's still here who presented. That was great. And thanks, Rajri, for organizing.
Sure, thank you.
Okay, bye, everyone.